All right, everybody, this is number 17. 17 is probably the most difficult one on the test. So you have a combination of lead-2 nitrate and sodium iodide. I'm going to assume that you know that if I mix those two things together, the potential precipitate is lead-2 iodide. Then the lead-2 iodide would go into equilibrium. It looks like this. And if the concentration of the lead and the iodide are greater than that is allowed by the KSP, there will be a precipitate. And if it's less than that, there won't be a precipitate. So we got to find out how the ion product compares to the KSP. To do that, we need to know the moles of lead. So we know that we have 100 milliliters, which is 1/10 of a liter. So 0.1 liters of lead nitrate. Now, since we know that there's only one lead in every lead nitrate, whatever the number of moles of lead nitrate are, that will be equal to the number of moles of lead. So we got 0.1 liters times 0.05 moles per liter. And that gives us 0.005 moles of lead. We need to do the same thing for the sodium iodide. So we have 0.2 liters of sodium iodide. We know of NaI, I'll put that on there. And we know that we have 0.1 moles per liter. That's a point right there. My smart board's not cooperating. So I end up with 0.002 moles of I minus. This is not a Brinkelhoff, of course, because it's an ion. So now we know moles of lead, we know moles of iodine. Just as a little aside, not a part of this problem, I'll put it in blue. If this was magnesium chloride, and you're looking for the moles of chlorine, or maybe I should say, if this was magnesium iodide, just to be consistent, and you want to know the moles of iodine, you would do the same process, but at the end, the moles of iodide, I minus ions, equals 2 times the magnesium ions because of this 2-to-1 ratio. So you have to be aware of that. Not part of our final problem, though, so we'll just take that out of there. Of course, if you want to see that again, just back up the video.
Michael Johnson, call extension 6600. Michael Johnson, call extension 6600.
Next step in this problem is to find the molarities of each of these ions. And our total volume is 100 milliliters plus 200 milliliters, so we're going to divide both of these by 0.3 liters. And that gives us then a concentration of lead ions of 0.0167 moles per liter. And down here, I give a concentration of iodide ions of 0.067 moles per liter. Big M, of course, means moles per liter. So now we're ready for the ion product. The ion product is the same expression as the KSP, so it equals the concentration of the lead ions multiplied by the concentration of the iodide ions squared. We know the lead is 0.0167, and we know the iodine is 0.067 squared, which gives us an ion product of 7.5 approximately times 10 to the negative fifth. Since the KSP is equal to 1.62 times 10 to the negative fifth, we can see that IP exceeds the maximum concentrations allowable by the KSP. So, yes, there will be a precipitate. So a precipitate will form. You have to note that this is not really a stoichiometry problem. You've got a beaker of one thing and a beaker of another thing, and you're pouring them in to a common beaker. So it's going in there, it's going in there, and then we're considering the concentrations that result because we poured them together, not that result because of a chemical reaction. That's why you don't use the mole ratios and look at the amount of lead nitrate and sodium iodide and so on. All right, that's the end of problem 17.